Hello everyone and welcome back for part 3 of chapter 21. In the last two videos we discussed the definitions of electric charge along with Coulomb's law, which allowed us to calculate the magnitude of force between two charged particles. And then we also saw an example problem of multiple particles in a system and how we would combine the net force of all of the individual forces in a system as they act on one particle, which was basically a glorified physics 1 problem. So now what we want to do is we want to move away from the individual particles to a larger macroscopic system. And what happens when we have larger and larger systems of particles, for instance, I'm going to use some red and blue dots on the screen here. If the red dots represented positive charges and the blue dots represented negative charges, and we were to ask what is the net charge of the system, well, if each dot is of an equal magnitude of charge, we would go through and we would count up all the red dots, which there would be 1, 2, 3, 4, 5, 6, 7, 8, 9 red dots. And there are 1, 2, 3, 4, 5, 6, 7 blue dots. And so we would have a net charge in the system of positive 2 because our positive charges exceed the amount of negative charges. So now that we have an excess amount of charge within our system, what is that excess charge going to do? And what are the positive negative charges in the system going to do? One way that we can think of this is assume you're going to a dance or something and you have individual pairs that are going to start dancing together, but eventually you end up with two people that don't want to dance with each other because they're not pairing off properly, and so they're going to act like some wallflowers and walk away. Well, same thing is going to happen with these charged particles. If we have an excess amount of charge, that excess amount of charge means that that excess is either all positive or all negative. We can't really have an excess of null charge, and that's what's happening inside this diagram. Every time we have a pairing of a positive and a negative, we produce what is called a null charge. But we have an excess amount of charge in the system, and so we need to see what's going to happen with that excess charge. So let's take a nice symmetric sphere, and we'll place some excess charge within that sphere. So we'll take a bunch of positive charges, and all those positive charges, they don't like each other. We know that like charges are going to repel, and based on Coulomb's law, we know that each individual charge will interact with every other charge in the system. Now there are quite a few charges in the system. It would take us a while to go through and add up all the individual forces and then figure out what the net force in the system is. But just remember that all of these charges don't like each other. They're repelling one another. Think of it like a big shoving match. As these charges continue to push each other away, ultimately the only direction that these charges can go is outward. And so these charges are going to forcibly spread themselves out along the edge of our sphere. And they're going to continue with their shoving match until they have achieved some form of equilibrium. And that equilibrium means that we're going to have a uniform distribution of charge at the surface of our sphere. And that's going to be a very important concept as we move forward in this semester, is the idea of uniform charge distribution. So I have the same amount of charge per unit area everywhere on the surface of this sphere. And you might ask, well, what about inside the sphere? And to answer that question, we need to be a bit more specific about the sphere itself, what the sphere is made of, physically how that sphere is constructed. So to help us out with that discussion, we need to discuss the different types of materials that we can use in constructing these larger macroscopic containers of charge, for lack of a better term. And so the first material that we're going to consider, so we have types of materials. The first type of material that we're going to consider is a conductor. And conductors will be a material that allows for free charge motion. And I'm gonna put free in quotations because it's not entirely free, but we're going to assume for right now that it is free. So what this means is that we have a material where if I wanted, I could place the charge on one side of that material and it could eventually travel to any other point within the material, given enough time and enough influence of outside forces. And we say free in quotations because it's not entirely free. Every material is going to have some amount of internal resistance to charge flow. Whatever this material is, whatever it's made of, it has to be made of some kind of element. That element is going to have a nucleus with electrons orbiting around it, and so having an individual charge trying to navigate this maze of other atoms, which are all surrounded by charges, this individual charge is not going to just travel through in a straight line. It's probably going to end up traveling through with a very randomized path, but it will eventually make its way to the other side. And that randomization, or that hindrance of the material to allow for the free motion, is what we will call resistance. And we'll explore that topic more when we get to chapter 26. So the second type of material will be a non-conductor, aka an insulator. And this will be a material that does not allow for free charge motion. And the idea behind a non-conductor is basically the same thing as a conductor, except that the amount of resistance that the charge encounters as it's trying to travel through the material is so high that the charge never actually makes it to the other side. At some point it just kind of gets hung up somewhere within the material, and it's not able to make it to the other side. Well, there are 4 types of materials that we're going to consider, and right now, given the descriptions of a conductor and a non-conductor, you might say, well, how can there be anything else? Either the charge makes it through or it doesn't. And so the third material that we're going to consider is what we call a semiconductor. And this is a material that can act like both a conductor and an insulator. Well, again, either the material allows the charge to pass through or it doesn't. It can't be both, or at least it can't be both at the same time. There will be times where a semiconductor will act like a conductor and it will allow charge to move through it, but then by making a slight change to the conditions of the semiconductor, we can turn it into an insulator, and then by undoing those changes to the semiconductor, we can revert it back to a regular conductor. Now there are different ways that we can manipulate these semiconductors to transition them back and forth between being a conductor and an insulator, and usually that involves something like a temperature change. So if you increase the temperature of your semiconductor, typically it will revert to an insulative state, whereas if you cool it down, it will revert to a conductor. And these semiconductors are very important because now you can have one object in your circuit that can do 2 things. It can act as an insulator or a conductor. So basically, you have yourself a switch within the material, and all that has to be done to turn it on and off is to vary the temperature. There are other ways that you can manipulate the properties of materials, pressure, electric field. There's a whole list of different ways that the properties of materials can be changed. In this case, the primary way is through temperature. And so maybe you have something in your circuit where if the current running through your circuit gets too high, the circuit gets too hot, and you don't want to burn out delicate components of the circuit, and so you put in a semiconductor that acts like a switch, and when that semiconductor gets too warm, it reverts to an insulator, and it stops the flow of current through the circuit, in essence protecting the more delicate components of that circuit. And then the fourth and final type of material is a superconductor. And this is a material that has free charge motion. No quotation marks. Free charge motion. Well, how can we have a material that allows for absolutely free charge motion? Well, if we go back up to the diagram here where we have our charge that's trying to get through this gauntlet of other atoms, how can we reduce the amount of interactions that that charge has with those other atoms? Because otherwise we end up bouncing around until we get out to the other end. So how can we allow this charge to move straight through the material completely unhindered? And for that, what we would have to do is we would have to reduce the resistance of the material down to 0. And the only way that we can do that is by supercooling the material. Usually this will require that we submerge the conducting material in something like liquid nitrogen or maybe even liquid helium. It depends on the material itself and how cold it needs to be before it can achieve that superconducting state. But once that state is achieved, we can continuously move charge through that material without the need of any kind of driving force. It's a very interesting concept where you can have charge moving through a circuit without the need of say a battery being connected to it. Now for our purposes in this class, we are going to focus primarily on the first two. This is an introductory course in E&M. The semiconductor physics would definitely be discussed in things like a computer engineering or electrical engineering course, and the superconductivity would also be for an upper level physics course, simply because the mathematics in describing what is actually happening during these transitions from conductor to insulative states requires quite a bit more effort. Whereas with the conductor and the non-conductors, we either have charge that's moving or we don't. So it's basically a binary case scenario for us. So with the conducting materials, if I have a sphere that is made of a conducting material, then any excess charge that I place on that conductor can move freely, in quotations. Given enough time, these charges will be able to move, and these charges will distribute themselves uniformly about the surface of that conducting material. If the material was an insulator, and I placed the excess amount of charge on that insulator, maybe I place a clump of excess charge right here on that insulating sphere. Well, the material is an insulator. It does not allow for free charge motion. So even though those charges don't like each other, even though those charges are going to be pushing and trying to force each other away, they can't physically move through that insulating material, and so they're just going to stay put. Now, some other things to consider when it comes to the structure of these items that we're going to be using. Are you working with a solid material? Is it hollow? So in other words, do you just have a shell? And so if we go back to the conducting material, maybe this first case scenario was a solid sphere, in which case the charge can move freely all the way through the entire volume of the conductor, but still that charge is going to continuously push all of the other charges away until we get to the surface. Because once we get to the surface, there's no more conducting material to continue moving through, and so the charge has to remain there at the surface. But what if we had a conducting spherical shell? Well, would the picture be any different? And the answer is no. The charge will still distribute itself uniformly about the surface of that sphere. So what about the insulator? What if our sphere was a solid insulator? What if I placed the charge somewhere inside the volume of that insulator? Well, because it's an insulating material, the charge can't move. The charge will stay right where it's at. The only way that I would be able to get that charge to move was if I came in and physically moved that charge myself. And so one possibility for this is, let's say I placed a large collection of positive charge on the surface of this insulating sphere. That charge will not be able to spread out uniformly like it does with the conductor because it's an insulating material. However, I could still achieve a uniform charge distribution if I were to physically spread that charge out over the surface of the sphere myself. And so what I would have to do is I would have to come in, physically with my hand, with like a rag or a washcloth, some kind of dry fabric, and just rub the surface of this insulating material. And as I do that, I would physically snag some of those charges and move them around the surface of this insulating material. So I would pretty much have to polish this insulating sphere with the rag until I got all of that charge to move around and deposit itself in a uniform distribution, because the insulating material will not do it by itself. And then we can also consider what would happen if we had an insulating shell. Well, the discussion would not really change. It's still an insulating material. Just because it's hollow on the inside, that doesn't change the fact that the insulator will not allow the charge to move on its own. If I want that charge to be uniformly distributed, I will physically have to come in and move that charge around myself. So now that we have these two different materials for consideration, we're not going to limit ourselves just to spheres or shells. We need to consider really any kind of geometric distribution of charge. I could have a rectangular conducting material, and if I were to place some excess charge on that rectangular conductor, the charge itself would have to distribute itself uniformly about the surface of that rectangular prism, for lack of a better term. If I had a pyramid, the charge would have to distribute itself uniformly about the surface of that pyramid if it was made of a conducting material. So the great thing about having these conducting materials is that the charge will effectively take care of itself. The charge will continue pushing on all of the other charges around it until it has reached this uniform distribution. And it is that uniform charge distribution that is going to make our lives so much better when it comes to the math that we're going to do. Because the next thing that we are going to do is we're going to take these considerably large collections of charge, and we're going to have to figure out the physics of these situations. And right now, the only thing that we really have available to us is Coulomb's law, and Coulomb's law only works with two charges at a time. Now we're talking about having large macroscopic collections of charge, which could be tens of millions or billions of individual particles, and we just don't have the time to sit around adding all of those up. So we need to find a more effective means of mathematics to tell us what is happening with these systems. And that's actually going to begin in chapter 22. We're going to bring up the idea of electric field. And we're going to start deriving expressions for the electric fields that are produced by different distributions of charge. But until then, I would like to finish up this video with a discussion of charge distribution on different spheres, along with the attractive repulsive force that can exist between some of these larger macroscopic systems. So we'll go ahead and take two large spheres of radius r, and these spheres will have identical geometry. They'll be made of the same conducting materials. So these are both conductors. And we're going to place an excess amount of charge on each of these spheres. And because we're going to have such a large amount of charge on these spheres, the author with our book has a tendency to call these larger collections of charge capital Q. So lowercase q can be a smaller collection of charge. Big Q is going to be a bigger collection of charge. But we'll go ahead and put in some values for these. We'll say that charge 1 is 500 microcoulombs, and charge 2 will be negative 200 microcoulombs. Because these spheres are made of conducting material, the excess charge on each of those spheres will distribute themselves uniformly about the surface of each sphere. And since charge 1 is positive, I will draw a bunch of positive signs there to indicate the distribution of charge. But charge 2 is negative, so we're going to see a negative distribution of charge about the surface of that sphere. And I would like to know what is the force present in this system? What is the force that is acting on each of these spheres? Now, each sphere has a collection of charge, but up until this point, we've only been able to work with individual charges concerning Coulomb's law. So if we were to use Coulomb's law the way that we've been using it, then every individual charge that I have on the first sphere, I would have to consider how it is interacting with every other charge on the second sphere, and then I'd have to move on to the next charge in line, and I'd have to figure out how it's interacting with every single charge on the second sphere, and that's going to take forever. And we don't have that long. So we need to find a better, more efficient way of using Coulomb's law. And the way that we're going to do this, we're actually going to piggyback off of an idea that we had back in Physics 1 that we called center of mass. So the idea of center of mass was that we took a mass of some uniform density. Actually, it didn't even have to be a uniform density, but it was easier if it was of a uniform density. And the center of mass was a theoretical construct where we took all the mass of the object and we shrunk it down to a single point inside the mass. And we called that the center of mass. And then any mathematics that we had to use with respect to the mass of that object, we could just assume the object to be a single point mass. And if the mass was of a uniform density, then it became very easy for us to find it, because all we would have to do is make some half cuts throughout the different axes of the material, find out where those half cuts intersected, and that would be the center of mass for that object. Well, we're not using mass anymore, we're using charge. And because these are all conductors, we already have the uniform charge distribution. Or if you'd prefer, you could say that we have a uniform charge density. And if we were to go through and make some half cuts through this sphere, every time we cut it in half, we would have the same amount of charge on each of those half cuts, and so the center of charge for this sphere would be located right at its center. In other words, we could take this entire macroscopic sphere and we could shrink it down to a single point charge of value Q1. Likewise, with sphere 2, we could take the uniform charge distribution of charge 2 and shrink it down to a single point charge value of Q2. And now we can use those inside of Coulomb's law. The only thing that we really have to be mindful of is that with Coulomb's law, right now there would be a certain separation distance between those two charges, but we have effectively shrunk those charges down to individual points that exist at the centers. And so the separation distance between the two charges will now have to incorporate the radius of each individual sphere. So maybe we call this R1 and R2. We said they were going to be identical, but the full radius that is going to be inserted into our force equation will have to be the combination of the two radius values and the separation distance between the spheres. So we can treat uniformly charged spheres like point charges. There's really no fancy math that is required. We could go through a triple integral or a 3D integration process, adding up all of the charges and seeing where the center of the charge for the systems would be, but that's probably a good 2 or 3 pages worth of Calc 3 that we really don't need at this point. If we just stick with the concepts of the uniform charge distribution, then we're good to go. All right. Now, we have one more thing that I want to touch on, and that is that now that we have charge 1 and charge 2, we can go ahead and plug these values in. Since I know what the individual charges of the two spheres are, we can say that the radius of each sphere is 5 centimeters, and maybe we have 20 centimeters of separation distance between them. All right, all of that information can go into Coulomb's law. Oops. Coulomb's law right there. And we can get the magnitude of the force between these two charged spheres. Now, charge 1 is positive, charge 2 is negative, so we know that these two spheres will be attracted to each other. So my next question is, if we allow these spheres to move under the influence of these forces, eventually they're going to come together. And as they get closer and closer to each other, the separation distance between them becomes smaller and smaller. And that means that the attractive force is going to become stronger and stronger. Eventually, these two conducting spheres will collide. They will touch. And once those spheres come into physical contact with one another, there is now a physical bridge where the positive charges can start interacting with the negative charges, and we're going to start seeing null pairs. In other words, we're going to start seeing some of the positive charges combining with some of the negative charges, and a plus and a minus results in a null charge. Well, we're not going to get a complete null charge for this system because we don't have enough of each type of charge to fully cancel everything out. Our 500 microcoulombs of positive charge and our 200 microcoulombs of negative charge will result in a final excess of positive 300 microcoulombs, which now has to be shared between the surfaces of the two spheres. We still have excess charge. That charge is going to have to distribute itself about the surface of the spheres. And because the spheres have the same geometries, because they have the same radius, they have the same surface area, Each of these spheres is now going to have a new charge value, which is equal. We have to take the remaining charge and equally distribute it over the remaining surface area. So each of these spheres now has a new charge value, charge 3, which will have to equal half of the remaining charge. So sphere 1 gets half of the remaining charge, sphere 2 gets half of the remaining charge. Well, what happens now? Now both spheres are positively charged, and they're both positively charged by the amount of 150 microcoulombs. And so what's going to happen is that each sphere will now be repelled by the other because they now share the same sign notation. And I've written Coulomb's law here with a q squared, and that's because the magnitude of each sphere is the same. But this is an interesting situation because we started with the two spheres being attracted, but then once they came together and they were physically able to bridge that gap and start mixing together their excess charges, we now end up with a repulsive system. And we can definitely plug those values in to figure out what that repulsive force needs to be. The only question is what would the R value be for the separation distance between the spheres. It can't be 0, because if it was, the math would blow up. Well, keep in mind that we're still going to be treating this as a system of particles. And so we're going to take the charge of each sphere and we're going to collapse it down to the center of each sphere, and that means that the separation distance between the two is just going to be 2 times the radial value of each sphere. And so that's what we're going to have to plug in there. But then once these spheres start repelling each other, that R value is going to start becoming larger and larger and larger, which means the repulsive force is going to start becoming smaller and smaller. All right, that actually brings us to the end of the chapter 21 material. So when we come back, we will begin chapter 22.